Welcome to this Chapter 40 video, where I discuss file system implementations, or how the structure is actually maintained within a particular file system. Let's begin. So, as you remember from a previous video, we talked about how a file system is part of either the entire storage or a partition within the storage. We're going to dive a little bit deeper into a particular partition where a file system resides. So I have two file systems that are demonstrated here. There's the ext4 file system, which is fairly common for Linux, and there's the NTFS file system, which is common for Windows. Now, most file systems will have a particular part of that disk that is always in this, or particular place in that partition that is always in the same place in that partition, called a superblock. Windows NTFS has a partition boot sector, but it serves the same purpose. I'll refer to it as a superblock. This superblock defines the file system. Such informations as where you can find the file metadata. In this case, under Windows, it's called the master file table, as well as where can you find the actual file data itself. In this case, I have a data stream. Now, the superblock is actually, on a Linux system, frequently divides this full system into what are called clusters. Each cluster having a certain number of files represented by the file metadata, as well as the data of that file. This is actually in order to reduce fragmentation within the system. NTFS does a similar thing. They have clusters, but I don't represent it here within this particular diagram. Now, we'll talk more about this metadata later on. There is a significant difference between the metadata that's stored within an ext4 system as opposed to the metadata that's stored within NTFS. But it is still basically the same type of data. File names and unique file identifiers. Those unique file identifiers have information about where to find the data within the actual storage. So we're going to step back a couple versions of ext to the ext2 file system. ext2 is just simply a less complicated version of the ext4 file system. So if we look here, we can actually see how this particular storage is set aside. Each entry here is one block, 4K if you will. Sometimes it can be 512 bytes, but we're going to use 4K blocks. And there are 64 of these particular blocks. This means I have 256 kilobytes within this particular partition, within this file system. Now the file system is mostly composed of the data blocks being the blocks where the actual file data is stored. But there is certain blocks that are set aside for specific purposes. There are blocks that are set aside for the inodes, these inodes referencing the file data. There's also a block set aside for the superblock. Again, the superblock defines where to find all this information within the file system. There are two other blocks we'll talk more about called the bitmap blocks, an inode bitmap and a data block bitmap. These bitmaps have ones and zeros that identify where a block is free or an entry is free and where it is used so that we can quickly allocate a particular inode or a particular data block. I've shown you what the file structure within an operating system is, but let's see what that is actually looks like on the storage itself. Every inode has a particular structure to it, and in this case, this structure looks a lot similar, very similar, I should say, to the stat structure. It has things like the inode, the mode bits, the size of the file, various times of that particular file, the group ID and user ID, the link count, how many links there are to it, how many blocks are allocated for this file, various flags that are set. But this is the largest portion of this file, this 60-byte area called the block. Block is actually pointers to the data block. The first 12 blocks in the ext2 file system point directly to a data block. So for the first 12, 0 through 11, that actually gives the, I should say those entries store the block number where the data is located. So for any file that I create that is under 4K, that's going to be contained within the first block or the 0 entry. When it comes past 12 blocks, and I'll show more of this, we actually go into what is called indirection. The index number 12 block, or the 13th block within this inode, is a single indirection block, meaning it is a pointer to a block that has pointers to data blocks. We follow that with a double indirection and a triple indirection. This may not make sense, but I'll describe it in more detail. So, how do we handle this multi-level indexing? Well, when we first create the file and blocks 0 through 11 are actually used, so block 0 starts the first 4K of the file. By the time we get to block 11, we're actually at file offset 45,000 or 45 kilobytes. So up to the first 45, 50 kilobytes, we can actually just simply reference each block using the block entry within the inode. But once we get past about 50K, we need to actually start using the first level of indirection. This block index points to a block on the disk, and this block actually contains indexes to other blocks. So let's say that I have just written my this 4K into data block 11, and I'm about to write byte number 49152. Well, the operating system will allocate this block and also allocate this block, putting a pointer from this to this block within the first level of indirection, and put a pointer into that. So in order to find byte 49152, if I choose to read that byte, the operating system needs to first read this particular block to find the actual data block. There can be up to 1,024 entries within the first indirection block, meaning that with just the first indirection, we can handle files up to 4 megabytes in size. Now the next level of indirection, or block 13 points to a block that points to blocks, but these will be index blocks that point to data blocks. Now that we've got 2 levels of indirection, we can have files up to 4 gigabytes in size. Finally, the last block, block 15, or I should say block 14, there are 15 blocks here. Block number 14 will actually have 3 levels of indirection. First level will contain 1,000 entries. Each of the next levels will contain 1,000 entries, and then the third level will contain 1,000 entries each pointing to a data block, allowing for file sizes up to 4 terabytes. As you can see, these allocating things via these blocks is actually a fairly efficient way to get to much larger file sizes, much larger than the 50K we would have if all we had were 12 indexes to blocks, or even just simply one indirection, which allows us 4 megabyte files. So multi-level indexing is the method used by the Linux or the most Unix operating systems to find data blocks for files. So let's talk a little bit about some of the things that are happening in file systems. In general, most files we find are relatively small. 2K is actually a fairly common size, and if you think about a 2K file fits perfectly within the first block pointer of an inode, meaning that we don't necessarily need any indirection for most files on a file system. But the average file system, or the average file size, is actually growing. 200K is pretty much the average these days. And with 200K, we can still fit everything in one level of indirection. So it's a fairly simple process with the vast majority of files on average. Most bytes on the file system, though, are consumed by large files, easily in the gigabyte range, if not larger. File systems can handle that with 2 levels of indirection, and even 3 levels of indirection allow us to have files that are just inconceivably large. That most file systems have up to 100,000 files on the file system, which is just an absurd number of files. Let's talk a little bit about directory entries. So directories themselves are actually special files. These special files have what are called directory entries. Each directory entry has a couple of pieces of information. Specifically, it has to have a name, and it has to have the unique identifying number, or inode number, for that particular file. You can also have information such as how long is the total record and how long is the string for the file name, so that you can have variable length strings. But not all directories support these extra pieces of data. Clearly, the most important piece here is the the name of it and the inode number. Now, these directory entries are very rarely ordered. You can see here that foo in this directory comes before bar. Very little is sorted. The actual ls command sorts the directory entries within a particular directory for you. It is not automatically done by the operating system. In fact, most APIs, including the opendir and the readdir APIs, present you the directory entries in the order they're found within the directory file. Let's talk a little bit about the inode in use, the data and inode in use bitmaps. These are sections of the disk, and I swore that I had a slide on that. I do. I'm sorry. So let's come back to this slide earlier, where it actually shows a kind of a zoomed in view of blocks 0 through 7 here. There's the super block, which is the first 4K. There's an inode bitmap that is at 4K going to 8K, and there's the data block bitmap, which goes from 8K to 12K. So let's go back to this particular slide. This slide shows a very small bitmap. These bitmaps are usually just simply ordered bytes of data. In this particular case, we have 8 bits across and 4 down, so we have 4 bytes of data. This 4 bytes of data can represent 32 either inodes or data blocks. When a bit is set to 1, that means that block or inode is actually occupied. If it's set to 0, that means that entry is free and available for use and can be allocated. So within one 4 kilobyte storage, we can safely track 32,000 entries, which means for a file system with 200,000 files, all we need is 6 blocks or 24 kilobytes to keep track of which particular inodes are allocated and which ones are not. Of course, when it comes to data blocks, this becomes very, very difficult and unwieldy to work with, which is why we cluster inodes and data blocks so that we can have a limited number of bitmaps for a particular set of data blocks. So let's talk a little bit about file access. Now that we understand that there is one inode per file, that there is a bitmap in the file system that keeps track of which files are allocated, which blocks and inodes are allocated, as well as the actual data blocks themselves. Let's see how these things are accessed. I'm going to open and read 12 kilobytes from a file at /foo/bar. In order to do this, what happens is first the root inode is read. That's what the root directory, so that this particular inode helps point to where the root directory data is located, where it gets read. At that point, inside the directory entry, there is an inode entry for foo. The foo inode entry is read from the disk, and the foo inode points to a data block, which is read. So now the foo directory has been read, and we can search the foo directory for a file named bar. So what happens is when bar is found in the foo directory, there's an inode, and we can read that inode now. This is just simply the open operation for a particular file. When we read the first 4K, it reads the bar inode to find out where the block is that needs to be read, then reads that block. It then writes to the bar inode. It's writing to the bar inode because we just accessed this file. We actually read data from it, so it needs to update that time within the bar inode. The read that happens after does the same number of steps. Reads from the bar inode, reads from the data block, and writes to the bar inode. So we can see how many reads and writes are happening within a file system just to read 3 blocks of data. So what happens when we write to a file? Well, that becomes even more complicated. Again, we read from the root inode, read the root directory data, which points to the foo inode, and the foo inode points to the foo directory data. And once we've found that, we can go ahead and create an entry within the foo directory. How do we do that? Well, first we look for an inode that's available. We read the inode list, and we write to the inode bitmap. So the inode bitmap tells us what free entries there are. Once we've found a free entry, we write back that we are using that entry, and then start writing to the foo directory to indicate we have a file name, which is bar, and we have an inode number. So we write that to the foo directory. We also start reading the bar inode to modify it and write the modified data for that inode bound, as well as write our access information into the foo inode. Now, every time we write a block to the data, first we read bar's inode, determine that we need a data block, which necessitates opening the data bitmap, finding a free block, and writing that we've allocated that block back to disk. We then write the 4K of data to the data block for bar, and then write our inode back to the file system for bar. And that happens for each of our 4 different writes. So clearly, writing is a very intensive operation, especially when it comes to actually modifying the bitmaps for both inodes and data. So our last topic is going to be about caching and buffering. Caching and buffering are 2 ways we manage to make an operating system and a file system more efficient. Caching is where we actually keep popular blocks in memory for quick access. We cache files that are being read, like program files, from disk into memory so that they can be quickly accessed rather than constantly having to read data from the disk. For example, when you start an executable program, it doesn't just simply load the 1 block you need to work with. It loads several blocks into memory, anticipating that you're going to actually be executing instructions beyond the first 4 kilobytes of that program. There's a lot of caching that goes on for files that are accessed, especially whenever it comes to the bitmaps for inodes and data blocks, because those IMAPs are frequently looked up and modified, and so it's good to have those cached in the system to find out where we can find, as well, not just the bitmaps, but also the inodes for very popular directories and files that need to be referenced fairly frequently. We find that memory paging systems and file caching are often combined within the modern operating system, so that whenever caching of files needs to happen, the memory paging system can do so quickly um, in order to maintain the memory paging system and make sure there's not a lot of um, blocks or memory pages that need to be unloaded and reloaded whenever memory gets filled up. Caching is making sure blocks are in data so they can be quickly accessed. Buffering, on the other hand, is a way of limiting the number of writes you make to a storage device. When we buffer, what we're doing is we're taking the changes for a particular file and storing them in memory temporarily, not writing them immediately to the disk. That way, if we make lots of very small writes, we can actually quickly modify that data in memory rather than having to wait the long time it takes to actually modify storage. This can lead to inconsistencies and corruption when you have a system crash or a power failure. This is why an operating system crash is a bad thing, because if you have data that is buffered and the operating system crashes, well, it was the operating system that was maintaining that buffer. Thus, any changes could be lost, or they may just simply be partially written. It is always a good idea, for safety's sake, if you want to validate that the data is being written to disk, to use an API called fsync. Fsync will make sure any buffered data gets written to the disk and any changes within the file gets loaded into memory. This brings me to the end of this Chapter 40 discussion of file system implementations.